Phases of matter in solutions is a fun little subject. You would think that there's not a whole lot that we can do with regard to funeral science in terms of the phases of matter, but it's really quite intricate and quite fascinating itself. So, we know, beginning with gas molecules, because if we think about it, the first stage of decomposition is bloating. So bloating involves a lot of gas molecules. And we know that these gas molecules are in motion. These gas molecules and atoms do not stop. They are constantly moving. The rapid movement of the gases account for the property of diffusion. Now, diffusion is a fun little subject in and of itself. Diffusion basically says that if you open a gas tank container into a room, eventually you're going to be able to smell it across the room. Formaldehyde diffuses in the air very well. So this is why you've got to have this good ventilation. Without good ventilation, then you're going to have all that formaldehyde getting into the air. And the last thing that we want is to begin to cross-link the proteins in our lungs and in our body by inhaling formaldehyde. So we need to also understand that diffusion occurs from a greater to a lesser concentration. So if I have, let's go ahead and kind of draw this out. So I've got a container. Let's make this container. And it's full of formaldehyde. I'm going to call it just formaldehyde. And I put this container into our virtual classroom. So we'll take this thing. Let's see if I can do this. I think I know how to do this. So I take this container, I make it really small, and then I put it on a desk. I put it on a desk in our virtual classroom. Okay? And then, kind of far away from where you're at right now, you're over here. Dressed in your appropriate work attire, right? And you're seated over here working on your, so here's your chair. Got good posture, great job. And you're working at another desk over here. And here's your laptop. And you're working here. And you're very happy about doing your work. And you have this smell. Eventually what's going to happen is some of that formaldehyde is going to start traveling. And as that formaldehyde begins to travel, you're going to smell it. And then once you smell it, oh, good gracious. Uh-oh. You don't lose your head. What happens is it doesn't make you very happy. And if you keep smelling it, it really doesn't make you very happy. Because then what's going to happen is you are going to fall out of your chair, ka-thunk, and be dead. You have to have good ventilation. Because with good ventilation, when you have a great fan that is spinning, what it does is it can take all that formaldehyde and it can begin to get rid of it. Now, is it going to get rid of all of it? No. But the concentration will be small enough to where now then, in our beautiful little classroom, you can still be working at the desk. You can still be alive. And though you might be smelling it, it ain't going to be too bad. Even in the midst of this room where we have an open container of formaldehyde. Now, I would never recommend that you have an open container of formaldehyde because then that's just awkward. Okay? But that kind of illustrates that diffusion. Eventually, that room will fill up with enough of the formaldehyde to cause some negative health effects because the room has less concentration than does the beaker. So let's think about this. In our little example there, the room has less formaldehyde than the container that contains the formaldehyde. So the formaldehyde, because it is volatile, that means it evaporates quickly, it's going to diffuse through the room. So these collisions actually provide pressure. Let's think about it. Think of these collisions as a small punch. If you have enough punches, you get a lot of pressure that can get built up. And when these gases under a lot of pressure have a whole lot of collisions, it can keep the tire inflated. Now, pressure is very interesting because it is this force per unit area. So if you multiply by area, you get the force, and you find out that all sorts of things have pressure. The atmosphere exerts a pressure on everything in it. Barometric or atmospheric pressure is called barometric because it's measured with a barometer like you see at the right, where you use a little bit of mercury as the old school way of doing that. We don't do that so much anymore. We have standardized ways of measuring things without having to deal with the toxic chemical called mercury. Now, this pressure gets to be something very interesting when we deal with decomposition. Because remember, the first stage of decomposition, you start the enzymatic breakdown and so forth, but thereafter you get bloating to occur. So we find out that when pressure increases, volume can be decreased. Okay, so let's think about this. When you squeeze a balloon, what do? As you squeeze that balloon, it gets harder and harder and harder to squeeze the balloon. The pressure goes up. It's pushing against you. This is Boyle's law. So let's think about this. Let's do a quick, simple calculation. As pressure goes up, the volume has to go down. So with this, if my pressure is 1 atmosphere, because that's what we blew the balloon up to. We can't blow it up to 2 atmospheres because the balloon would keep expanding, right? So we blow that balloon up to 1 atmosphere, and let's say that balloon has 1 liter in terms of its volume. So this is P1 times V1 is equal to P2 times V2. So let's think about this thing. If the volume goes down, so now then we're at 0.5 liters, so we've squeezed that thing down to half a liter. Then what is P2? When we solve for x, x is equal to 2 atmospheres. We've increased the pressure. So that's interesting, but how does that play into bloating? All right, so let's think about this. When we start dealing with bloating, we still got this P1. We've got to times a volume 1, and that's equal to a P2 times a volume 2. So bloating, by definition, is where the volume increases. So let's say we have a pressure of 1 atmosphere. So this is an example of increased bloating. Okay? We have a pressure of 1 atmosphere upon death. And let's call it a volume of, we'll make it very generic, a volume of 1 body. Fair enough? When we look at things, when bloat happens, you get an increase in the amount of volume, right? So let's say you're not going to double the volume of the body, but let's say we have a significant amount of bloat and we're going to increase that by, instead of 1 body, we'll call it, I'm going to convert it to fractions, if that's okay. Let's work with me here. So we'll call it, let's see, 4/3 of a body. Okay? So what is our new pressure? Well, when we do this, what we find is our pressure is equal to 3/4 of an atmosphere. So the pressure actually went down. So this is lower when the volume, the bloat, increases. So remember, diffusion moves from greater concentration, that's how much stuff, to lesser concentration. So what happens here with bloating is, now then, the bacteria that are responsible for the bloating, let's think about this. These bacteria that are sitting in the body, now then, what happens is that body got a little bit bigger, didn't it? So we'll go ahead and let me show you this. This bacteria is in this body, and the body's about like that, okay? So now then, as we move this way, the body gets a little bit bigger. As you get more bloat, and initially the way that happens is you don't get a huge amount of growth in bacteria, but the body gets a little bit bigger. Not hugely bigger, but a little bit bigger. Now then, the bacteria have more room to work, and the bacteria can propagate a little bit more. And as they propagate a little bit more, what happens? You get more bloat because they produce more gases. And as that happens, you get more decomposition to occur. And so you start to see that it becomes a process where Boyle's law with diffusion ends up increasing your degree of decomposition. So, is there a way that we can keep the volume from going up? Well, interesting to ask such things. Let's look at something different. At higher temperature, you get more volume. So this is called Charles' law, okay? This is Charles' law right here. It's the basis of a hot air balloon. You heat up the gases, they expand. Never ever heat a sealed container, that's awkward. Because then the container explodes. And it follows this formula right here. This V1 over T1 is equal to V2 over T2. So let's think about this. Remember what we had a while ago with our example of the bloat. We have V1 over T1 is equal to V2 over T2, okay? So we went from a volume of one body, right? And that one body is at 37 degrees C, okay? Because that's the temperature that a body expires at. And then after some bloat occurs, the volume goes up to 4/3 of a body, so it increases by 33%. That's fairly reasonable. Is equal to some temperature. Let's solve for that temperature. So we do a little bit of cross multiplying and whatnot. So then we get T2 times one body is equal to 4/3 body times 37 degrees C. The bodies cancel because they're on the opposite sides of each other. So then we can look at what 37 times 4 divided by 3 equals. Now then that temperature goes up to 49.3 degrees C. At that temperature, a lot of the bacteria just begin to start, they can't live. They die. At 106 degrees C, or 106 Fahrenheit, which is about 41 degrees C, something like that, 42 degrees C, we end up seeing a lot of bacterial death. So that bloat is going to increase that temperature as the volume goes up. So higher temperature increases the volume, right? Or higher volume increases the temperature. And so what's going to happen is you're going to, as that temperature goes up, you're going to increase that volume. So if temperature increases, a temperature increase can cause a volume increase. How might we shut down that volume increase and shut down that bloat? Well, what if we do a temperature decrease? What's going to happen? That will cause a volume decrease. And a decreased volume means what? Less bloating. And that is why we typically try to store bodies, if we have to store them for a long time, in a refrigerated container. That's why morgues exist. Interesting stuff. There are 3 states of matter. We're going to switch from gases now, exclusively, to other things. So gases are always moving, all which direction. They have you can increase or decrease pressure, And one of the things that you find is gases are compressible. So a body that is 33% bigger due to bloating actually has compressed gases. That's why you don't want to like push on things or anything like that, because it can cause explosive eruptions through different bodily orifices. Be careful with all that stuff. Instead, we want to make sure that we can release such pressure, if need be, in a very controlled manner. However, with solids and liquids, those are not compressible. Because these are not compressible, they are called, they don't have near as much movement. They don't have freedom of motion. So they have less freedom of motion. Now, granted, you do have some of these molecules in the liquid phase evaporate, but it's only the surface level that tends to evaporate. And granted, you can have some of these solids melt or do something called sublimate, but that's going to be very limited. And then that depends on temperature. So notice that all these things are temperature dependent. You see it says heat or cool. So there's something interesting here, and I want to kind of walk you through what this is. To heat, so let me do it this way. Boop doop. All right, here in this corner. I can take a gas and I can convert that gas to a liquid. When I convert that gas to a liquid, that is called condensation. When I go backwards to a gas, that's called evaporation. Okay? Now, I can also take a liquid and turn it into a solid. As I do that, that is called freezing. And when a solid becomes a liquid, that is melting. There's nothing new here, except sometimes you can take that solid and turn it into a gas. That is called sublimation. And you see that when snow at freezing temperatures slowly decreases in volume. That decrease in volume is a sublimation process of the snow into atmospheric water vapor. And you can take some of that atmospheric water vapor and you can deposit it in a process called deposition once the air temperature gets below freezing onto roofs and cause a frost. So this is kind of a neat little phase triangle for you that kind of shows you the different processes of phase transitions. So I'll call it a phase transition triangle. Make sure you kind of are aware of this. All right, so those are our three states of matter, how they can be transitioned from one place to another. For a liquid, by heating or decreasing the pressure, you can produce a gas. by cooling or increasing of pressure, you can produce a liquid. Now, liquids are more dense than gases because they are held closer together than gases. So they have something called cohesive forces. These cohesive forces are sometimes called things like surface tension. But these cohesive forces are a little bit more interesting than just surface tension. These cohesive forces have something to do with how molecules interact one with another. So particles in a solid are in a fixed pattern. They're crystalline. Liquid particles are stuck together, but they're not in a fixed pattern. We can move one molecule throughout a cup. Gases move independently of the other atoms or molecules, but oftentimes with these liquids, they have to kind of get passed around. So the stronger the attractive forces, the higher the boiling point. In other words, to convert a liquid to a gas, it takes a lot of energy to do such things. So it's more likely to be a liquid than it is a gas. Water is one of those things. So if I have a little bit of water, which is HOH, and I've talked to you a little bit about this, maybe. You might remember it. I've got several water molecules in a container. We'll just make it like this. Be simple. These water molecules, each one of these oxygens has a negative charge. And each one of these hydrogens has a little bit of a positive charge. You remember the delta plus, delta minus? Okay? As a result, we have the positives can go and be attracted to those negatives. And the negatives can be attracted to the positives. But what happens when you have a couple of positives that get kind of close to one another? Well, something I didn't show. I have an oxygen that can pop in there. And this oxygen, having the lone pairs that it's got and the negative charge that it's got, can kind of do this and bind there. So you start to see that you have different bonds that are not full bonds, but are kind of little bitty bonds. Each one of those things are called a hydrogen bond. Because you have a hydrogen that's partially positive that's attracted to an oxygen that's partially negative. What this results in is if I want to take this one little water molecule right here and I want to pull it, I want to take this molecule and I want to remove it from the system, I have to break this bond and I have to break this bond. It becomes more difficult to remove that water molecule from the system because you're having to break hydrogen bonds. So now then, what do? Well, to do this, we have to add more heat. When you're adding more heat, that is what we were talking about last time, where it is endothermic. You have to add more heat. This process of removing, the water has to suck heat out of the surroundings in order to evaporate. So that is why we sweat and we get cool, because the water sucks the heat out of the surroundings, i.e. our skin, and cools us so that it can evaporate. It's an endothermic process. Requires a lot of energy. So, we have to overcome all these forces, and in this case for water, hydrogen bonding, by using this energy. Now, let me talk a little bit about volatility. I mentioned it briefly with the formaldehyde example earlier. Volatility basically is how easy is it for a liquid to become a gas. Volatility is ease of evaporation. The higher the boiling point, the less volatile a liquid is. Formaldehyde has a very low boiling point, and so it is very volatile. Water has a higher boiling point. It is less volatile than formaldehyde. And glutaraldehyde also has a fairly high boiling point, so it's less volatile than formaldehyde. Therefore, it tends to be safer if you are in a closed, non-air handled environment. So, you have to not worry about things like a body evaporating because it's not very volatile. But you have to worry about your formaldehyde evaporating, so don't leave a volatile formaldehyde container open. These liquids can evaporate and become gases without boiling. I've already mentioned that. That's that sweat process. After some time, the amount of gas that is condensing is the same as the liquid evaporating. This is a dynamic equilibrium here. That dynamic equilibrium means it moves back and forth, back and forth, back and forth. Do you remember when you were younger and you're working in one of your grades, whatever grade that was, and you had a container? And in this container, that was a sealed container, what you did is you had a plant, and you had dirt in that container, and that plant was growing out. Probably a bean or something like that, styrofoam cup, all that kind of stuff. And then what happened was you'd get all this water that would condense on the top of the container and on the sides of the container, so it was hard to see the container because you'd have water all up in there. You remember seeing that kind of stuff when you were growing up? You're building up this greenhouse that has a... So what happens is you have water that leaves and evaporates, and other water that comes in and falls back down and condenses. So you got to see this dynamic equilibrium work out with your little plant. This happens all the time in nature. We get this dynamic equilibrium. This is a closed system. Water can't be added to it, nor can it be removed. Now, one of the neat things is we find out that these changes of state are reversible. See, this is that phase transition triangle that I was talking about. You can go back and forth and back and forth, back and forth. Just because you're solid doesn't mean you can't become a gas. Just because you're liquid doesn't mean you can't become a solid. So it all depends on how the molecules move, how much energy. So this depends on energy and those molecular forces. Because those molecular forces will get things close to each other, and then they can interact with one another. Gases don't interact. They're too far apart. Too far. But these liquids can interact pretty easily. And the solids are all just stuck. So what are the types of cohesive forces? Well, I like to call them, these cohesive forces, the more generic term, I like to call them intermolecular forces. We already talked about hydrogen bonds. Hydrogen bonds are when you have hydrogen bound to an electronegative atom. Typically, nitrogen, oxygen, sometimes sulfur. So what that does is you end up with a delta positive hydrogen and a delta minus of the electronegative atom. And then you can start to have an oxygen here, and a hydrogen here, and a hydrogen here, and you end up with this hydrogen, this delta positive, interacting with a delta negative oxygen on these other molecules. That kind of makes sense. So you can also have something called dipole interactions. So with dipole, what we're seeing is polar covalent bonds from differing compounds that interact. So an example of that might be, let's go back to ethers. Do you remember ethers? Where you have some R group and an O and another R group here. Remember this? And then you've got this ether that has a delta minus here, and these things are a little bit delta plus. So whenever you've got another ether, where you've got an O and an R and an R, and this thing is big delta minus, and these things are little delta pluses, and this is little delta plus, we get a little bit of interaction. We get some interaction right here. This here is that dipole interaction that I'm talking about. And the last one that I want to mention, because there's only 3, this one is called dispersion forces. And these dispersion forces are kind of fascinating, because basically what it says is, if I have a molecule, we'll do it this way. If I have a molecule, it's going to take up a certain amount of space. And this molecule, if it runs into another molecule, what happens is, as this one molecule is moving around and whatnot, as it approaches this one here, what happens is the molecule's electron cloud shifts. And then what we're left with is this one becomes delta minus and this one's delta plus. Just because this molecule was moving closer to there, to the other one. Now, interestingly, as that happens, the one molecule on the right, it gets shifted too. And so we end up with a delta plus over here and a delta minus over here. These are called induced dipoles. And that's just because the electrons that surround molecules can be distorted. So they kind of get pushed. It's kind of like their, what do we call this? We could talk about social distancing. If one of these molecules gets within 6 feet of another molecule, the one molecule will try to back up. We polarize the one that is being approached. This is an induced effect, an induced dipole. So these three intermolecular forces that involve hydrogen bonding, dipole-dipole interactions, and dispersion forces really begin to show how molecules interact one with another. So, we talk a little bit about that, giving you some interesting examples. All things have dispersion forces. Now, water is quite unique because it has a molar mass. Its molar mass is 18 grams per mole, right? But it's still a liquid. The molar mass of CO2, which is a gas, is 44 grams per mole. Interesting. Well, and that's because water has lots of cohesive forces, intermolecular forces. The intermolecular forces it's got is hydrogen bonding. Now, one of the things I didn't tell you about things up here with these intermolecular forces, this is the highest force, and dispersion has the weakest force. So let's label this strongest, weakest. All things have their own personal bubble. So, interestingly, water expands when it freezes, and it has a strong surface tension. That means here, water kind of likes itself. It wants to hang out with itself. So, while we're talking about water hanging out with itself, what about solutions? Solutions, as we talked about way a long time ago, is a mixture of two or more substances that are not chemically combined into a compound and can have variable composition. Salt water, right? We can have really salty water, or we can have kind of salty water. Or let's think about this. Sweet tea. Sweet tea is one of those things that is chewable in some places in the country. In other places, they call it sweet tea. I don't know if they put any sweet in there. So, we also find out that we have lots of different types of solutions. So these solutions, this is the definition for a solution, okay? This defines the solution. And you also have heterogeneous solutions that they're not uniform throughout. They are a nice little mixture of stuff. So a great heterogeneous solution, let's think of this. Granite is a heterogeneous solution. It's a solid dissolved in a solid. But you can see it's not quite uniform, is it? But it's still granite. You can also have homogeneous solutions. Those are consistent throughout. A great example of a homogeneous solution, as I just mentioned, is sweet tea. So, these solutions are comprised of a couple of different things. So you notice it says 2 or more substances that are not chemically combined. So a solution is comprised of 1, a solvent, and 2, a solute. So a solvent has the highest concentration. There's more solvent than anything else in that solution. So if you have an aqueous solution, there's more water than anything else in that solution. A solute are in lower concentration, and they can be anything else. You can have lots of solutes in one solution. See ocean water for an example. So, with these, oh, we already talked about that. Talked about that. So now then, to talk about solubility, to be a solution, it has to be homogeneous. So a heterogeneous mixture would be granite. A homogeneous mixture would be sweet tea. Or an emerald. A good emerald, if it's homogeneous and is crystal clear, is worth a lot of money. So you've got to be homogeneous. Solubility. Basically, there's a rule about solubility. And here's the rule. Like dissolves like. So let's think about this. Water will dissolve salt. Okay? Oil will dissolve let's call it the extract of oregano. When you put these two things together with some other stuff as well, like sugar, what you get is Italian dressing. But only the oil dissolves the extract of oregano. The water will dissolve the salt and sugar and vinegar and all that other stuff, right? The oil is on top. So you won't get that nice, salty, great flavor if you don't shake up your Italian dressing first. You have to shake before serving. Otherwise, you're not going to get the full flavor. Water solutions are aqueous solutions. Alcohol solutions are called tinctures. Let me go ahead and tell you this. This right here, you need to know it. I've actually been told by one of your previous classmates in years past that they really appreciated me dwelling on tinctures. A tincture is an alcohol solvent. This is something that we don't talk too much about these days because they're not very common. Back in the day of my grandparents, they used tinctures all the time. Like, for instance, a great tincture would be vinegar as the solute and isopropanol rubbing alcohol as the solvent. This thing can be used for eardrops. You know what that does? It's antibacterial. So if you've got swimmer's ear, using a mixture of white vinegar dissolved in isopropanol as a tincture is a great thing to stop that infection. Memorize the fact that a tincture is an alcoholic solvent. There are other types of solutions. You can have liquids and dissolved in liquids, right? Like I just said, the vinegar and alcohol. You can have gases dissolved in liquids. This is like carbonation. You can have solids dissolved in other solids, such as what you see in stainless steel. And you can have gases dissolved in other gases, like air. We've talked about that one before. For the liquids dissolved in a liquid, if it can't be dissolved, it's considered immiscible. Oil and water, not dissolvable one in another. Therefore, they are immiscible. But if you can dissolve it in any amount, do you see this? Any amount, it's said to be miscible. Oil and water are immiscible. But if you can dissolve any liquid in any amount in something, we call it miscible. There are lots of types of mixtures, and this is a great thing to memorize. Great tool, usable for you. You have the aqueous solution. You have tinctures, miscible solutions, immiscible solutions, suspension. You find this suspension a lot. It's a mixture of materials that'll settle out and can be filtered out like a muddy water. But if you do this right, you can build a suspension like, hold on, let me think about this. There's a lot of makeup, specifically bases, to give good coloration. They're actually suspensions or emulsions. So they have two insoluble things or a mixture of things that aren't actually dissolved in one another, but dispersed. Eventually, these things will separate over time. That's why bases only last for so long in the makeup world. This is really important. A lot of these emulsions, a lot of these suspensions will help you out in the funeral business. Electrolyte solutions are things that contain ions. So, maintaining a good electrolyte balance is critical to making sure that the cells are not hypertonic or hypotonic. A hypertonic cell or a hypotonic cell, when doing the embalming, will sometimes disrupt the embalming process. So what you really want to do is to make sure in your pre-embalming fluids that your pre-injection fluids, that you maintain a good electrolyte solution. Otherwise, it isn't going to work very well. The cells will not be optimized, and you'll have to use some hydrating agents or some dehydrating agents later. Using a good pre-injection fluid will minimize your work later on. As I said earlier, like dissolves like. Polar and ionic solutes can be soluble in water. Remember this. Things that are nonpolar, like gasoline, dissolve in nonpolar solvents. In fact, there's actually a number of murder mysteries that are based on that concept alone. Water dissolves these ions well. Look at this. Do you see that water? The delta positive hydrogens that are hanging out with that chloride that's negatively charged? How about this? The delta minus, let me fix that a little bit. How about this delta minus oxygen that's associated with that positive sodium? That association helps them to dissolve well in one another. This is that dissolution or solubility that we're talking about. Solvation, right here. Solvation, that is the process of dissolving. That becomes something that may show up on your board. Just like you can have diffusion in air, you can have diffusion in liquids. So like ink and water, or how about this? Not ink and water, but let's think about this. Dyes in water. Does that make sense? So, whenever sometimes you were doing the embalming, we need to add dyes to make the body look more, look more alive or less gray. So we'll add reds and blues and stuff like this, predominantly reds, and as a result, or yellows even. As a result, what you end up having is a dye that can be diffused throughout the entirety of the body. This is important to maintain good coloration, this diffusion in liquids. But they dissolve more slowly through the solvent. It takes a while. You can't rush it. This was an important thing for one of my former roommates who was trying to do an embalming one time on a lady that had passed away in the hospital. She'd been in intensive care for some time, and the family, when asked, said that she died of natural causes. Well, my old roommate, who was in training at the time, went to embalm her with standard embalming fluid with formaldehyde, and she was extraordinarily overweight, and he couldn't find a good vein. And so he ended up finding one in her ankle and began to do the embalming process there. Well, what happened was, after a little while, he noticed that her leg was turning green. So what was happening is the bilirubin was being converted with the formaldehyde into biliverdin. Rubin, of course, means red, verdin meaning green. So she was turning Kermit the Frog green. Well, very quickly he realized his mistake. He shut down the embalming as fast as he could, which means he pulled him from the tubes. Called his boss, and his boss started laughing. And he said, "Let me guess. Family said that she died of natural causes." And he said, "Yeah, that's exactly right." "She was in the hospital for some time?" "Yeah." "What color was she?" "She's kind of yellow." "Mm-hmm." "She died of liver failure, probably from too much alcohol. Family doesn't want to say she's an alcoholic, so they said that she died of natural causes." What you're seeing is that conversion of bilirubin via formaldehyde into biliverdin. Oh, gotcha. Fortunately, that dye did move slowly, and so they had an open casket for that funeral. But had he embalmed her in the standard injection places, there would not have been an open casket, and they would have that funeral home would have been sued. All right. So solutions always have a concentration. And this concentration is how much stuff is there. It's like formaldehyde, concentrated formaldehyde is formulated at 37% by mass. So that means if I have 100 grams of solution, I've got 37 grams of formaldehyde. That's kind of nice. This is a percent by mass. You can also do percent by volume. Now, percent by volume is a little bit different. Percent by volume says that at 37 grams of formaldehyde in 100 grams of solution, we actually have 40% formaldehyde. So these things, percent by mass, does not equal percent by volume. As a result, we need to make sure that we understand what kind of concentration we're working with. So, Fruit juice is delivered by volume. Alcohol, drinking alcohol, is by volume. Sugar solutions are by mass. You also have this fancy term that chemists use called molarity, which is moles of solute per liter of solution, which is not going to be something that you need to deal with in your profession as funeral directors. You also see parts per million or parts per billion, or sometimes milligrams per liter of solution, milligrams of solute per liter of solution. But most of the time, we're really working with this percent by mass because of the nature of your business. So this is an example of the molarity. Notice that we can look at 20 grams of NaCl in solution. So we convert the 20 grams of NaCl into moles of NaCl. Notice that the grams canceled there, and we're left with moles. So 0.34 moles divided by 1 liter gives us 0.34 molarity. Again, you're probably not going to mess with this, but you're going to be messing with it in terms of index. Index is the embalmer's term for percent by mass. So this is the way you're typically going to be using this. Index is grams of formaldehyde and 100 grams of solution. So if we're using a concentrated formaldehyde solution, which most of the time you're not, you'll be using a dilution of some sort. We say that formaldehyde at a concentrated formaldehyde solution has an index of 37. So what happens if we need to... There's an interesting thing that you can do. Sometimes with this index, you need to actually dilute stuff. So let me go ahead and show you this real quick, and then I'll call it quits. I know I'm running long on this particular lecture. So there's this formula, M1V1 is equal to M2V2. So if I have this M is your concentration, V is your volume, okay? So your concentration, your initial concentration is typically your M1, and your M2 is your final concentration in your final volume. So let's think about this. If we have an initial concentration of our formaldehyde of 37, and what we need to have is a final concentration of 3.7. This is index, okay? This is an index. When you have an index of 37, we need an index of 3.7, and we need 1 gallon of this. Okay? What volume of that 37 index am I going to need? This is a typical dilution type problem. It's nothing terribly fancy. It says I start with an initial concentrated solution of formaldehyde of 37, and finally I end up with an index of 3.7. What volume do I need? Well, you divide both sides by 37. So V1 is equal to 3.7 times 1 gallon divided by 37. So the volume that I need is 0.1 gallons. So 1/10 of a gallon of a concentrated solution of formaldehyde will give me 1 gallon of my reduced index. This is more appropriate. That 3.7 is a lot more appropriate for embalming than a 37. And it's safer to use in a closed space, such as an embalmer's room. That said, I know it was a awesome lecture, a little long,